So scientifically, where are we? Where are we in the course? What have we learned? What are we learning? So we started, let's recall what we're trying to accomplish here. We started learning about rates of change. We learned about rates of change, both on average. So an average rate of change is you have some function. This is y equals f of x. I have a graph of a function, but really I'm thinking of a function. I have some start time and an end time here, and let me make it slightly higher here. And so the average rate of change we observed is what? The slope of the secant line, right? I have this secant line. The average rate of change is slope of a secant line versus an instantaneous rate of change. We're back. Okay. Where were we? We learned about rates of change both on average, but the average rate of change is the slope of the secant line, as opposed to the instantaneous rate of change. The instantaneous rate of change is the slope of the tangent line, right? So slope of the tangent line. So rate on average, secant line on average from x equals a to x equals b. That's the kind of thing we would do on average, as opposed to instantaneous rate of change at, as opposed to from, at x equals a. Okay, so that's this. So that is the slope of the tangent line. And the problem is, how do you get a tangent line? If you just write down a tangent line, you get 0 over 0, right? The rise is 0, the run is 0, you're at the point x. And so that's why we needed limits. So instead of tangent line, we interpret the tangent line as the limit of secant lines, limit of slopes of secant lines, slopes of secant lines. And so that's why we needed to learn about limits. So we needed to get really good, needed to master limits. So that's what we had spent the first little bit of the course on. How to take limits of all kinds of things. No matter what comes up, we know how to take a limit. We know what it means to take a limit. Limits tell us about continuity and continuous extensions. This is all review. Extensions. Can you read anything that I'm writing? Sometimes. If you can't read something that I'm writing, please tell me to write slower. Continuous extensions. We learned about things like the intermediate value theorem. We learned about things like the squeeze theorem. Okay, and we learned about asymptotes, limits at infinity, asymptotes, even oblique asymptotes for a second. We talked about that. Right, so now we're really good at limits. So let's go back and use our newfound mastery of limits to study now this question in much more detail. Instantaneous rates of change. So back to tangent lines and their slopes. And let's get really, really good at those. Okay. Let's go back to my favorite example, y equals x squared. So let's make that our function, bless you, for the next couple of minutes. So we had computed the slope at x equals whatever, how about 2? So what's the slope of the tangent line at x equals 2? How would we set this up? So slope of tangent line. This is still review, right? I think we even did this. At x equals 2, let's go over here. The slope would be what? It's the limit of something. Tell me again. Rohan. Yes. So one way of doing it, sorry, just a second, Ron. One way of doing it is to think about a small distance h. So this point would be 2 plus h right here. And then we would look at what the secant line is, and that's how we're taking this limit. Go ahead. Right. So this height is the point 2 plus h in the x coordinate, and the corresponding y coordinate has to be 2 plus h squared, because that's what happens to any point on this curve. It's a point x comma y where y is x squared. So if the x value is 2 plus h, then the y value is 2 plus h squared. So go on. So it's the limit of 2 plus h squared minus 2 squared. Exactly, f of x is 2 squared. So that's here. This point is 2 comma. I'll write it as 2 squared, even though we all know that 2 squared is 4. So that's the rise. That's how much the rise was divided by, yeah, either h, or if I'm going to be pedantic, I'll say 2 plus h minus 2. Right? That was the run. The run started at 2 plus h, or ended at 2 plus h, started at 2. So that's rise over run expressed in this way. And what Rohan is telling us is that we can do this in general. We can say it's the limit, or we can just, in this particular case, we can record what we're doing. If our function f of x is x squared, then all we're doing here is taking f of x, so that's f of, or rather f at 2 plus h, subtracting off f at 2, and dividing by, well, we know that this is going to be 2 plus h minus h is just h. Okay? Does that make sense? Let's just evaluate this limit just for fun. I know this is going to be easy for you guys. So it's the limit as h goes to 0. 2 plus h quantity squared is 2 squared, which is 4, plus 2 times h, which is 4h, plus h squared. So I've just squared out 2 plus h, 4 plus 4h plus h squared. That's 2. Then I subtract off 4. That's this. I divide by h. Okay, the numerator, so this is the limit. Please don't drop your limits. It's the limit as h goes to 0. The 4s get to cancel. That's you. There's an h on top and bottom that cancels. And again, it cancels when h is not equal to 0. And so I get, it's the limit of 4 plus h as h goes to 0. And that limit is 4. No surprises. Okay, so that slope of this tangent line right here has slope. I didn't draw it so well. It should have slope 4. It looks like it's less than 45. It should be quite a bit more than 45 degrees by the time. Okay. Any questions? This is all review. Good. Okay. There's another way that we could have done this. Instead of thinking about h going to 0, moving some distance h, we could think about a nearby point instead of x equals 2. So here's x equals 2. And then we could have a nearby point just called x equals u or something. Another way we could have done this is take the limit as x goes, as u goes to 2, 2 being the point that u is converging onto. I'm just giving you one more way that we could have thought about this. And then it would be, instead of f of 2 plus h, we can think about f of u minus f of 2 divided by u minus 2. Okay, so this is the new rise, this is the new run, and instead of h going to 0, we have u going to 2. Exactly the same thing. Again, this is review. No questions. Questions, Sid? No. Okay. It's up to you which way you prefer. Let's just do it both ways so that we get good at either way. So this will be the limit as u goes to 2. F of u is just u squared. F of 2 is 2 squared. That's 4. Divided by u minus 2. Now we recognize the top and bottom because we're really good at limits. We recognize this is u squared minus 4. That's a difference of squares. And so there's a u minus 2 on top and a u minus 2 on bottom, and a u plus 2 left on top. I'm doing this a little quickly, but I think you guys are all with me. Anybody not with me? Okay, everybody's with me. So this is the limit as u goes to 2 of u plus 2, because I'm canceling a u plus 2 on top and bottom. I'm factoring this as u plus 2 times u minus 2 and canceling the u plus 2 on top and bottom. Canceling the u minus 2 on top and bottom, leaving it just the u plus 2, and the limit of that is the same 4. As u goes to 2, u plus 2 is 4. Okay, two different ways you could have done the same thing. Whichever way you prefer, some people like this algebra better, some people like this algebra better. It's the same thing, two different ways to do the same thing. All right. We could do this at any point. Instead of doing it, instead of doing doing this, instead of computing the slope of the tangent line at x equals 2, we can do it and do the same at x equals 3, or x equals 2.5, or x equals 1, or x equals -7, or x equals some constant. What's your favorite constant? The correct answer is C. You were going to say C, right, Annabelle? C. 4 is your favorite number? Most people choose 7. All right, we'll go. So the point is now everybody gets to have whatever favorite number they want. We'll do this at any value C. Okay. Do you have a preference if you want to try to compute the limit using h going to 0 or u going to? You guys like h to 0? Interesting. Okay. I'm going to try to convince you that in this case, we'll do it both ways. But I think in this case, the other one's actually easier algebra. All right. So again, what's going on? We have our function y equals x squared. I don't know where c is anymore. C is over here somewhere. The height, so this point is c comma c squared. We've moved a little distance, so this is now c plus h. We can kind of do both at once. Let's not do both at once. Let me not confuse it. Here's the new height is, this distance, this height, let me do it like this. This distance is c plus h quantity squared. And so a slope of a secant line, so the slope at x equals c, slope of the tangent line to the graph of y equals x squared at x equals c is equal to the limit as h goes to 0 of the rise is c plus h squared minus c squared. I'm taking the difference between this height and that height. That'll give me this height. So c plus h squared minus c squared. And what's the run? Yeah, c plus h minus c. C plus h minus c, also known as h. You want to take a minute and try to do this calculation? Take a minute. Anybody not know what to do? How to even get started? No, everybody's hard at work. Good. Anybody got it? Okay. We're still writing. Still working. Raghav, how'd you do it? Yeah, you expanded the square, so I get c squared plus 2ch plus h squared. Yeah. Then I'll leave the remaining c squared, I'll leave alone. And then the denominator is h. So I cancel the c squareds, cancel one of the h's, and I get the limit as h goes to 0 of 2c plus h. And this function has a very nice limit as h goes to 0. It's just 2c. How many got that? Awesome. 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 Okay. What if you had done it the other way? What if you had done it with u's instead of c's? That would be the limit as u goes to. Should I draw a picture? Or so instead of thinking about the distance being h, just think about this new point being u. Yep, exactly. As u goes to c of, what's the height here? U squared, exactly. I subtract off the height here, which is still c squared. And the denominator is u minus c, exactly the run, right? Rise over run, u minus c. Oh, but that's, again, super easy. It's the limit as u goes to c. It's a difference of squares. So all that's left when I cancel u minus c on top and bottom is u plus c. And what happens as u goes to c? I just get c plus c. Well, that's 2c. Let me ask again, which way do you guys prefer? Limit as h goes to 0 or is limit as u goes to c? Okay. In this case, I do prefer u goes to c, but there are other cases where I prefer h going to 0. So you should be able to use either one. Okay. They're completely equivalent. They give the same answer, right? We got the same 2c either way. They're equivalent methods. Be flexible, be agile, be able to use either. Okay, so what does this mean? What have we learned? If we take, right about there. Okay, if we take, so what's the conclusion? The slope of the tangent line to the graph y equals x squared at the point x equals c. At any point c, all you have to do if you want to know the slope is double it, is 2c, is double it. So in other words, if I draw this graph, y equals x squared again, y equals x squared, at any point x, if this point is 1, the slope is going to be 2. So that's a slope of 2. If the point is 2, the slope is going to be 4, exactly as we computed. We computed the slope. The reason this answer is 4 is because 4 is double 2. That's why we got that 4 last time. Okay, this slope is going to be 4. How about it? X equals -1. The slope is -2. You still double C. The slope here is going to be -2. Here, the slope is -2. How about at 0? Twice 0. 0. The slope is 0. Because right at that bottom, the function y equals x squared isn't changing at all. It's just flat line. Okay? But wait a second. What have we actually done? We've gone from a function, y equals x squared, and we have a new function. Because what is it if we ask for the slope of the tangent line at any value c, and the answer is 2c, well, that's a function that takes c and gives back 2c. Right? What's a function? It's an operation that does something. You give me a c, I give you 2c back. So that is what's called the derivative. So the function f, let me call it g of x is equal to 2x is the derivative of the function f of x equals x squared. What does derivative mean? You take grapes and you derive from grapes wine by a process, right? So there's some process that gives you something else from what we don't drink wine, whiskey. What do you guys get? Beer. You take barley, wheat, hops, water. You take water and you make water out of it. No, you take ocean water and you derive from it drinkable water by, burning off how do you do it? You heat it up and you heat it up so that the water turns into. You don't heat it at all? No, but if there's what's a desalination plant? These things exist, right? If you have access to spring water, but if you are surrounded by ocean water, no, you can't drink the ocean water, but there's desalination plants that take ocean water and convert it to drinking water. And I think what you do is you take the water, you heat it up, it turns into steam, but the salt doesn't rise with the, so you take that steam and you cool it back down, and now you have pure drinking water. It is so much work. That's why most places, if you can get spring water, you get it, but if you can't, then you use, there's this thing called desalination plant, right? I imagine that's what they do. Anyway, that's a derivative. Derivative is a process that gives you something else. So that's all this is. There's a process. We're discussing how to make wine. We've completely gone sideways here. Let's come back. Let's come back. Sorry, Sid. Is it math or we're just chatting? It is math? You want to tell me what it is? The power rule. Yes, we're going to get to the power rule. Yes, that's right. So some of you, again, have seen calculus already, and so you'll know that this is the derivative of this function. You've learned these things. Other people haven't, so we're going nice and slow, and we're going to get to things in a very systematic way. So they're really solid. So the derivative, the usual notation, so notations you'll see for derivative, notation, the derivative, instead of writing g, because g, how do I know what the original function was? Instead of writing g, I would write f prime of x is equal to 2x. This is the derivative function. Derivative function. Yeah, desalination plant, that must be what they're doing. Okay. Another notation you'll see, because it's the difference, there's a numerator difference and a denominator difference, people will write d dx. In other words, the difference, this is like a difference operator applied to x squared divided by the difference in, this is just rise over run, okay, to try to emphasize that what's happening is you're taking a slope, an instantaneous slope. So you'll see people write d dx instead of a prime to a function. So you write f prime if you know what f is. If someone gives you a function f, you write f prime for the derivative. Or if you just want to say what the function is x squared, then you can write d dx of x squared. You can't write x squared prime. That looks weird, right? But you can write d dx of x squared, and you can write d dx of f of x. You can also write d dx of f of x. That's perfectly fine. You can write dy over dx. Yes, dy over dx. This is, again, emphasizing that it's a change in the y. D is difference. So it's a change in the y divided by the change in x. Okay? And in the case of the function x squared, what we just computed is that the derivative is 2x. Okay? For any value x. So it's a little funny because we're used to thinking of x as the variable at which we, we use c as a constant. But now we have a function that takes c to 2c. Well, that's a function that takes any dummy variable. You can think of this as being c going to 2c, but traditionally you write x going to 2x. Okay, does that make sense? Question? All right, let's compute a bunch of derivatives. You understand what a derivative is? It's telling you the slope of the tangent. Let's do something. Let's do something a little off script. So here's, again, y equals x squared. Here's our parabola. What if I graph the derivative function? What does the graph of y equals 2x look like? Yeah, it's a function at 1, it's at 2, and at -1, it's at -2. So it's this function, okay? So the graph of the derivative function doesn't really look anything like the graph of the original function, but it has all kinds of information. So for example, you know that here, the function y equals 2x passes through 0. That's a place where the slope is locally 0 of the original function. So the graph of the original function is flat. Does that make sense? That's the kind of thing you can You can see. Let's do another one. Here's a random function. Y equals f of x. What will the graph of y equals f prime of x? I want to now graph. Let's do it in another color. I want to graph on top of this y equals f prime of x. I don't know. I haven't given you any values for the function. I haven't given you an equation for the function. But what we're asking for is, what does the derivative look like? So how can we try to draw such a thing? One easy thing to start with is, where is the function flat? Because wherever the original curve is flat, the derivative will be 0. So where is this curve flat? It looks like it's flat right about here, right about there. So there is going to be a 0 of the derivative function. Where else? Here-ish, right about there, it's flat. So that's going to be a derivative 0. Does that make sense? What's happening to the slope here? It gets negative, and then it gets less negative until it goes back to 0. So the slope gets negative, and then it gets less negative until it gets back to 0. You see that? You guys starting to get a hang of this? How about what's happening here? The slope starts getting more and more positive. We start out flat, and pretty quickly we get a positive slope. So that would be the derivative function rising up. How about to the left of this point where it was flat? The function stays pretty flat, but the derivative is starting to get the slope. What's this slope? Positive. And that's this slope. It looks like here, the way I drew it, it's like straight up. Yeah, so it's really, really positive. So it's taking its time getting positive, but then once it gets positive, it gets really positive, really fast. You see that? So just knowing the shape of a function, you can roughly put some things together about the shape of the derivative function. The derivative function carries the information about the location, about what's happening to the curve. We want to know, where is it increasing? Where is it increasing by a lot? Where is it not increasing at all? Where is it decreasing? By a little or a lot? Where is it flat again and then it starts increasing? You guys see that? Let's go the other way. What if I give you the graph of the derivative function? Let's go the other way. What if I give you, here's some axes. Here's a derivative function, y equals f prime of x. So if that's the derivative function, take 5 minutes and try to sketch what you think the function might be. Y equals f of x. So try to give yourself like a 2-hump camel or something, and think about what the derivative function, if this is the derivative function, what might the original function that it came from look like? I want you to start getting a spidey sense for what derivatives are. Will.
It looks flat. So that means the slope is going to be. It's not changed at all. Your rise over rise. The rise, so it's not rising at all. The value of the slope, it's going to be equal to 0. Does that make sense? We're going to do a whole bunch more examples. I'm just starting to try to build your intuition. It's going to take a minute to get used to. Well, it has it's flat here, also looks flat there. And it starts getting negative, the slope is negative. And then the slope goes to 0, and then the slope is positive. We start moving up. Yes. So if you go just put the change line, what's that slope? Yeah, 1, 2, something like that. How about this? The slope would be this. Yeah, 10, 100. And here the slope goes to the right here. It's 0, and then it starts to get negative 1, you said, so it's 0, and then it's 1 again. So that's a bunch of numbers. Well, we can graph. That's for any x value. That's a value. We can graph. That makes sense. So then, if this is 0, the slope here is 0, and the function will be at 0. The slope there is 0. The function is going to be at 0. If the slope is negative, the function is going to be negative. Does that make sense? Now I'm asking you to do something much more different. Guess what the function looks like if I tell you something about it.
Let's try it together. Anybody got a picture? Can you do like something like this with your hand and tell me? Andrew, how'd you do it? Tell me what you were thinking.
Well, basically, I saw that for the first leg of it, slope is positive, becoming less positive until eventually it becomes negative for a bit.
Yep. Great. So let's just say that back. The slope is positive. It's positive. The slope. This is the value of the slope. So just because the function is decreasing doesn't mean the slope is decreasing. The slope is positive of our original function that we're trying to guess. So the slope is positive until it gets to here. Here we should see flat. The function should get flat. So the original function is doing whatever it's doing. It's increasing until it gets right to this point, and at that point it changes from being an increasing function to being flat to being a decreasing function until right here it gets flat again. So it's decreasing, then it gets flat again, and then increasing until right there. So right there, wherever that happens to be, it's increasing until it gets flat again, and then decreasing until it gets flat. Wherever that is, it's decreasing until it gets flat, and then it's just increasing. Okay, did you have something that looks like that? So we can tell where it's increasing, where it's decreasing, and where it's flat, just by looking at the sign, just by looking at whether the derivative is positive or negative, right? That's exactly the information that the derivative is captured. Does that make sense, Annabelle? Okay, so keep that in mind as we compute a whole bunch of derivatives and try to understand the relationship between a function and its derivative. Who's totally lost? This is something that's going to take some night's sleep and reflection and homework to start getting your intuition about this stuff. Tell me again. David.
So the two, when you said that when that prime x
Yes.
down, why is the line going? Why is x going up?
Even though it's going down, it's positive. So right here, let's say the value here is 3. That means the slope here is going to be 3. And if here the value is 0.1, the slope is 0.1. 0.1 is still a positive slope. It's still an increasing function.
So why is f of x rising?
F of x is rising because the slope is positive. If the slope is 0.1, then I'm rising. If the slope is negative 0.1, then I'm falling. That's exactly the information the derivative is telling you. If you're measuring the distance from the wall, am I moving away from the wall or towards the wall? If I'm moving away from the wall, the distance to the wall, the rate of change in the distance to the wall is positive. I'm increasing my distance to the wall. If I'm moving towards the wall, my distance to the wall is decreasing. So the rate of change is negative. That's exactly what we're reading off of the derivative. Okay, it's okay if you don't get it right away. We're going to do a ton of practice problems about these kinds of things, and you'll get more used to it. Let's compute a couple more derivatives. All right, what are some good ones? How about 1 over x? Okay, let's do some more derivatives. Y equals 1 over x. So this will be our f of x. And let's see if we can compute the derivative f prime at some point. Now, we can say f prime of x if you guys are okay with that. In other words, now x is the variable. So 1 over x looks like this. It's a hyperbola. Y equals f of x. And I'm going to say, here's my value x. I used to write x equals c for some constant c. But what's the difference? X equals c or just x? Just leave it x. Okay? So if this is x, then this point is x comma f of x, right? This height is f of x. And if I can either take, what do you guys want to do? Take a nearby value x plus h, or do you want to take a nearby value u? How many want to do x plus h? Okay, how many want to do u? Okay, guess what? Do it your way. Take a minute and do it your way, and tell me what you get for an answer. Let's do it together. I'll do it slowly, but you do it your way. If you want to do x plus u, do x plus h, then do x plus h. If you want to do u as u approaches x, do it that way. We'll do them both. Let's see, which one should I do? Yusuf. Yusuf says you. Okay, sometimes we are a democracy, sometimes we're a dictatorship. Right now, Yusuf is in charge. Okay, so the derivative function of the function 1 over x, that's f prime of x. That's just the derivative. The prime means, people think the prime is like, the prime means just another way to say a number, to say that you've done something to the function. Like you have a constant c, you have another constant, c prime. You have another constant, c double prime. You have another constant, c triple prime. It's just an old-fashioned way of saying some other function. So this is some other function, but we can remember that it's related to the original function by using the same letter. Okay, so f prime is some other function. Its definition is that we take the limit as, what do we say? As u goes to x, the limit as u goes to x of the value of the function at u, so that's f of u, minus the value of the function at x, divided by, so that's the rise, that's df. Those of you that like to think about this as df dx or dy dx, same thing. Okay, so that's change in f divided by change in x. The change in x is y going from x to u. In other words, u minus x. Right? Anybody with me? Awesome. Okay, let's continue the calculation. Are you guys doing? You can do it on your own. You don't have to do it with me. Do it on your own if you prefer to do h going to 0 or u going to x. Oh God. Okay, so this is the limit as u goes to x. What is f of u? 1 over u. F of anything is 1 over that thing, right? So f of u is 1 over u minus f of x, 1 over x, divided by u minus x. If only we had just spent a couple of weeks getting really good at limits. Oh wait, we did. That's exactly what we did. So let's work this out. We just have to do a little bit of algebra. So limit as u goes to x of, I have these two fractions. What am I going to do with them? Annabelle. Yeah, exactly. I'm going to make a common denominator. I'll multiply both by what? So 1 over u is x over u times x. 1 over x is u over u times x. That's what you said, isn't it?
Yes.
Yes. Okay. So far, so good. We made a common denominator. And so we have the limit as u goes to x of let's see. I have an x minus u divided by ux, all divided by u minus x. So I have x minus u divided by ux, all divided by u minus x. I told you fractions are the killer. If your fraction stuff isn't like this, then calculus becomes impossible. So make sure that you're very, very comfortable with layers upon layers of fractions. Something divided by something divided by something else. Make sure you're not confused about how that division goes. Okay, keep going. Let's keep going. Okay, what do you notice? Yeah, I have an x minus u and a u minus x. So the ratio of the two is -1. Exactly. So this and this cancel with a minus sign. Yeah. So this is the limit as u goes to x of -1 over u times x. I dropped the negative. -1 over u times x. So now, is there any problem sending u to x? No. So what do I get? -1 over x squared. Okay. -1 over x squared. So the graph of that, what does the graph of that look like? The derivative function. Well, it also blows up at 0. For positive values, small positive values of x, what does this look like? Yes, Shirley? Oh, I thought you were saying. The question is, what is happening to this function when x is like 1? What's the value when x is 1? -1. Yeah, so it's -1. So the derivative at x equals 1 is -1. And how about for small values of x? Yeah, negative infinity, exactly. It's going to be a huge negative number. So it's this huge negative number, and then it gets closer and closer to 0. So what does that mean? The derivative is getting closer and closer to 0. That means the curve is getting flatter and flatter. Exactly. So that's exactly what we're seeing here. The slope is a huge negative number, and then the slope flattens out as we approach this asymptote at infinity. Okay, question?
So take the 0 as a third on the asymptote.
If you take where the derivative function is 0, so 0 is an asymptote of this function, which means that the other function also has an asymptote. I don't know where, but it has an asymptote. Yeah, we'll get to that. This is all I'm planting seeds. We're nowhere near any of this stuff. I'm trying to plant seeds well ahead of time. Okay, that's the derivative. Did anybody do it with x plus h instead of Jenny? What's the graph of 1 over x squared? We're back. How's the quiz going? Anybody? Okay, let me write this down here. Quiz. Yeah, let me record that 1 over x squared does that on the other side. Our quiz was compute f prime of x for f of x equals root x, and draw f prime of x. Okay, so f of x looks like this. Y equals f of x. Anybody got it? Jenny, you got it? Tell me again. Bye. Bye, Bob. Bye. Rohan got it. Okay, a bunch of got it. So Dan, tell me what you did. Everybody's done working on it? Okay, let's see how you did it.
So I did as the limit of u goes to x.
Beautiful.
So I did root u minus root x over u minus x.
Beautiful. Did everybody get that? If you got that, give yourself a point.
And then on the top and bottom.
Yes, I love it. I got the point. Yep.
And then on the top and bottom, I multiplied by root u plus root x.
Beautiful. Love it.
And then the top comes u minus x, which cancels cancels out at the bottom, and you're left with 1 over root u plus root x, and as the limit of u goes
Okay,
to x, it would be 1 over 2.
Slow down just a little bit. If you thought to do something like multiply by root u plus root x, give yourself a point. If you did the, if you canceled that top and bottom, give yourself another point. And finally, Dan.
And then as the limit of u goes to x, it's 1 over 2 root x.
Right. 1 over 2 root x. Okay, so give yourself another point for that one. What does 1 over 2 root x look like? What's the graph of that? Let's do. Yeah, 1 over x is like this. 1 over x to a positive power is like this. And 1 over 2 root x looks something like that. So it's going to 0. It's going to 0. Who asked that question before? What was your name again? Emil. Emil, you asked and I answered incorrectly. If the derivative is going to 0, is the function have an asymptote? So the derivative here is going to 0, and the function is rising ever so slowly, flattening out, but it's not an asymptote. It's still rising. Square root of x is just rising, rising, rising. It's just the rate at which it's rising gets flatter and flatter and flatter.
So what if the derivative function goes to?
If the derivative function goes to infinity, then the original function has to go to infinity. Because the derivative is saying it's increasing faster and faster and faster. Well, the only way to keep increasing forever is to blow up, just like the derivative blows up. Okay. Thank you for that question, because that gave me the opportunity to clarify what I said before was nonsense. Does everybody, does that make sense? Okay, hand your quizzes all the way to the end, please. And we'll collect them and pass them along. All right, let's do a couple more. Oh, we were going to do this 1 over x using x plus h. Should we do that? You guys want to do that? Nimmer, you don't want to do that. You like the other way better. All right, look at that. In just a couple of minutes, you guys have come around to you going to x. It's a little nicer for some things. For some things. You still, Andrew, you prefer, let me go next. Let me point out one thing, by the way. You could have been even sneakier here. Did anyone do anything different here, out of curiosity? What's your name? Ali. What'd you do? So yeah, I think I can't quite hear what you're saying, but I think what you're saying is you took u minus x and wrote it as root u minus root x times root u plus x, plus root x. That's what you did, yeah. So you pretended that u and x were both squares, and already here it's a difference of squares. Should I write that down? Let me write that down. Alternatively, here, root u, thanks Will, minus root x divided by u minus x is the same, leave the numerator alone, factor the denominator as root u minus root x times root u plus root x. Turn it into a difference of squares, even though u and x didn't start out being squares. They're the squares of square root of u, square root of x. Okay, then you can cancel directly and get to the same answer. All right, so great. Just wanted to point that out. There's a million ways to skin a cat. You can still say that as a anti-cat. I mean, a million ways to skin a cat. No, that's not an expression.
I heard it.
You've never heard it before. Oh my God, I'm hating myself. There can't be that many ways to skin. Moving on. Let's do another one. How about f of x? I don't know. Let's make up some functions. X over x minus 1. I have no idea what that looks like. We can figure out what that looks like, but let's do it. Let's do it all together. What do you guys want to do? U going to x or h going to 0? Shirley, you got one? H going to 0? Okay, just for variety's sake, let's do h goes to 0. So f prime of x is the limit as h goes to 0 of what? So in general, I take the value of the function at x plus h. I subtract off the value of the function at x, right? This is the rise. This is the value of the function when I shift over by a little value h, either to the left or to the right. I subtract off f of x and I divide by the run, which is h. In this case, this is the limit as h goes to 0. Oh God, f of x plus h. So wherever I see an x here, I have to replace it by an x plus h. Okay, it's not so bad. It's not so bad. So I have an x plus h divided by x plus h minus 1. Minus, so that was f of x plus h, minus f of x. F of x is x over x minus 1. And all of that I'm going to divide by h. Anybody? Everybody with me? Okay, now what? Common denominators. There's nothing else we can do. We gotta work out what's going on here algebraically. So let's make some common denominators. So I'll multiply the top and bottom of this by x minus 1. I'll multiply the top and bottom of this by x plus h minus 1. That's how I'll get my common denominators, right? Let's do it. So I have x plus h divided by x plus h minus 1, whoops, minus 1, and I'll multiply the top and bottom of that by x minus 1. So I'm grabbing this denominator and I'm multiplying the top and bottom by that denominator. So far, so good? I think you would have been the better, you going to x would have been the better way to do it here, but it's good to be able to do it both ways. Minus x, I'm going to multiply top and bottom, x and x minus 1. I'll multiply by this denominator, which is x plus h minus 1 divided by x plus h minus 1. Okay, that is the numerator. The denominator is h. Let me use a little fancy technology to put that h in front. Okay, it's not so bad. It's not going to be as bad as it looks like it's going to be. I hope. Let's go. Okay, so this is equal to the limit as h goes to 0. I have a 1 over h in front, which used to be here in the denominator. I just pulled it out of here, so it's not in our way. Okay, the denominator, there's a common denominator now, which is x plus h minus 1 times x minus 1. That was the whole point of doing this cross multiplication. So I have the same denominator here and here. What's the numerator? I got to multiply all this out. So FOIL this, x squared minus x plus hx minus h. That's x squared minus hx, plus hx minus x minus h. Did everybody get that for multiplying these two out? It's just a little bit of algebra. We're not scared of algebra. Minus, or maybe we are scared of algebra. Minus this, minus x squared plus hx minus x. Did I do that right? Okay. Now the canceling gun. X squared and x squared minus x and minus x. That's all I can cancel on top and bottom. There's an h. There's an h on the bottom here that I can cancel with these h's on top. And that, sorry? Oh, there's an hx. Very good. Let me, before I do that, before I do all of that, let me catch the minus hx and the plus hx. So those also cancel before I do anything. Okay. And now I have an h on the bottom and a minus h on top, which leaves a -1 for the entire numerator. The entire numerator has turned into -1. That was not quite so bad, relatively speaking. All right, sure. Nobody blame Shirley. It was my decision to do it this way. Okay, so I have a -1 on top I have an x plus h minus 1 on bottom and an x minus 1 left over. And now there's no problem sending h to 0. So this limit, so this derivative, the derivative of this function is -1 over, sorry, did I do something wrong? X minus 1 squared? All right. Let me quickly check if that's right. Bottom, we should graph it. Minus top times the root of bottom all over bottom squared. And yeah, that is right. Okay, so don't look at that. I'll show you what that is later. Good. That's the answer. You want to graph these two things? X over x minus 1. Where are we here? Desmos. So y equals x divided by x minus 1. Okay, that's this function, whatever it is. And its derivative, I claim, is -1 over x minus 1 squared. So y equals -1 divided by x minus 1 what happened to divided by? Divided by, oh, come on. Yeah, that would be smarter to raise it to the -2. Too late. X minus 1 squared. Okay, what are we learning from this? What are we learning from this? This is, in this case, we do have a horizontal asymptote here and here. So the slope of the derivative function is getting closer and closer to 0, but never actually getting to 0. And then the slope is very negative, which means the derivative here, sorry, the derivative is very negative, which means the slope here is pointing down. And here the slope is, again, it's getting closer and closer to 0 from below, which means the slope here is negative. It's just very slowly decreasing until it starts decreasing rapidly. Let me draw that again. Let me draw it again just on paper. So, whoops. So the original function y equaled what? X over x minus 1? X over x minus 1. So asymptotically, what's happening as x goes to infinity? It's going to 1. We're really good at horizontal asymptotes now. As x goes to -infinity, still 1. We have the same, we have the two asymptotes at x equals 1. We also have a vertical asymptote at x, sorry, y equals 1 are our horizontal asymptotes. We have a vertical asymptote at x equals 1, and then it basically does something like this and like this, whatever it does. Okay, what's going on with the derivative? The derivative, the slope here is always negative, but it starts out being pretty close to flat, and then it gets negative, then it gets super negative. It's always negative, so the slope is always negative, but it's very close to 0, and then it gets super negative. How about on this side? The slope here is also very negative, and it starts flattening out to be close to 0 slope. So it's also negative, but it's flattening out to be close to a 0 slope. And that's exactly what this function is. It's a function that has a pole, that has a singularity, it has a vertical asymptote at x equals 1, and then it's not quite even because it doesn't have the symmetry. The symmetry, what would have been an even symmetry, has been translated by 1. So it's like our 1 over x squared function, except translated. So it's doing this kind of, but it's always negative. It's never equal to 0, right? So this function, what we just learned, I mean, we could have seen maybe by other means, but this function is always decreasing. The function is decreasing here, it's decreasing here. It has this, it manages to jump from -infinity to +infinity when it crosses the x equals 1 vertical asymptote, but it's always decreasing, and its derivative is always negative. Cool? Everybody get that? You getting the hang of this? Do a couple more? Any questions? Couple more. Okay. All right. Here's a function. Here's a function. F of x equals 3. What is the derivative of that function? Everybody's saying 0, and I agree with you. If the function is always 3, then its slope is always flatlining. The slope is always 0. Could we do it from our definition of the derivative, the limit as either h goes to 0 or u goes to x of f of x plus h minus f of x divided by h. So what's the difference between 3 and 3? 0. The numerator is always 0. The function never has a rise. Over any run, its derivative is 0. Okay? So that's what's going on. Does it have anything to do with the number 3? No, the derivative of any constant is 0. Okay, so derivatives of constants, the derivative of a constant, derivative of a constant is 0. Okay. What if I have some complicated function? Let's say I have some function g of x. Here's g of x, y equals g of x, with its various slopes, increasing, decreasing, whatever's going on. And I have another function, y equals h of x, and it has its own slopes and slopes of tangent lines. What if I add those two together? So let's say that f of x, whatever. Oh, that's ugly. Ooh, sorry. That's better. Let's say f of x is equal to g of x plus h of x. Okay. How do I even draw the sum of two functions? Like here, the functions are both small and they're equal. But one is decreasing and one is increasing. I'm not really sure what to do with f. And I kind of drew it funny to make my life as hard as possible. But here it's like a negative value and a larger positive value. So f is going to be over here somewhere. Here, h is 0, so the sum is exactly equal to g. I don't know. I'm just going to make something up. That's what f looks like. How can I possibly try to figure out something about the slope of f, knowing the slope of h and knowing the slope of g? Seems complicated. Hold on. What are you thinking? That's an excellent question. Would it be possible? So can we learn anything at all about the slope of f, knowing the slopes of g and h? And Helen is suggesting, well, maybe we can compute those two slopes and add them together. Does that make any sense? Well, let's see. What would the derivative of f be? By our rule, it's the limit as, let's say u goes to x, just to vary it up. F of u plus x minus f of x divided by u minus x. I'm just putting in the definition of derivative, rise over run, in the limit. But f, for any value of f is always g plus h. Whatever the function g is, plus whatever the function h is. So this is the limit. Sorry? I'm sorry, thank you. That was the whole point of using, thank you. That was the whole point of using u, that I have one less thing to write. F of u minus f of x divided by u minus x. So that's the limit as u goes to x. F of u is g of u plus h of u. And I subtract off f of x, that's g of x plus h of x. And I divide that by u minus x. But wait a second. That's the limit as u goes to x of, if I group these guys together, I can write this as g of u minus g of x divided by u minus x. So that's grouping these. And I can group these together. So that's one grouping. Another grouping is h of u minus h of x divided by u minus x. But what happens to this ratio? You guys see what I'm doing? Raga. That's getting closer and closer to G prime. What's happening to this? That's getting closer and closer to H prime. And the limit, if two limits exist, then the sum is also approaching the same limit. And so the derivative of a sum is just the sum of the derivatives. Now let's think about that. If I know that G, I get money from selling apples and selling oranges. And I know that my apple sales are going up at a rate of $2 a day. And I know that my orange sales are going down by $1 a day. My net is the sum of those, right? My actual profit from those two sales is the sum of those two profits. Well, what happens to the rate of change? If I'm going up $2 in apples, I'm going down $1 in oranges. First of all, I should cut out the orange business. That's losing money, but whatever. I have $2 I'm gaining here. I'm losing $1 there. What's happening to me in the sum? In the net is $1, right? 2 plus -1. I'm getting $1 a day. So the derivatives, exactly, the rates of change simply add. It's exactly what exactly what we would hope to have happen. If you have a sum of functions, then the derivatives add. So now I can ask you, what's the derivative? Or let me write it in this way, just to mix up the notation. What's the derivative of the function x squared plus 1 over x? Do you have to do a whole bunch of arithmetic now? No, because we know the derivative of x squared is 2x. We know the derivative of 1 over x. We computed it. -1 over x squared. Done. Okay. Didn't we compute the derivative of 1 over x back here? Somewhere? Yeah, right there. -1 over x squared. That's where it is, -1. All right. Very good.